we'll try to stay on time, and if you have more questions that cannot fit in this 5 minutes, I just remind you that there is this meet the speaker session afterwards, where you can ask more questions. So I will ask all the participants to shut down the microphone unless you are the speaker. And at the end, if you have questions like yesterday, please raise your hand. Okay, and I'll give you the stage. If for some reason you cannot talk, the microphone doesn't work and so on, you can use also the chat, and I'll read your questions. But I think it's better if you ask your question yourself. It would be probably clearer. Okay, so let's start. So the first speaker is Axel Schild from Zurich, and he will talk about mini electron effects of strong field ionization described in an exact one electron theory. So please, Axel.
Thank you, Nicola, and also thank the organizers for this opportunity to talk here. I really like this online conference, actually. So I hope you can see me and hear me well. If not, please let me know. Yeah, so I thought I'm going to start with something that most of you already know, and this is the three-step model. Now, the three-step model is kind of a very fundamental model in attoscience, and it's the standard model that you have some kind of well, you have a laser field which induces some kind of ionization by tilting the potential. So this is kind of let's say an atomic potential or something like that. And here you have some kind of electron cloud, and there's a laser field coming, and this tunnel ionization happens where an electron is ionized. And in the next step, you have this continuum propagation where your tunneled electron, your free electron, is now moving outside of this core region and is only influenced by the laser field. And then when the field sign changes, the electron is accelerated backwards and is then hitting the parent ion, the core, I call it core. And this leads, in this case, to the generation of high harmonics. Yeah, it's one of the standard models in attoscience. Now, let's say you really want to simulate this. Now, a lot of you do this, and you know this problem. The fundamental problem is that this region here is actually not just one electron; it's many electrons. So you have to simulate many electrons, which in principle is possible for in a bound state region, of course. There are many methods for that. But at the same time, you also have to simulate this ionized part, which can move very far away. And so you also have to cover a very large spatial region, and you might also have to very low amplitude here, so very small amount of electrons there. So you somehow have to describe this together, and this is kind of a big challenge in the field, in which a lot of people work on. Now, what about this? So if we really want to look at this picture, yeah, this kind of a single electron picture. And also many calculations or many models are based on such a single electron picture. I call it the single active electron assumption, where you're saying you have a wave function of one electron, and this is now propagated in an effective potential with some additional interaction with the laser field. Now here in the length gauge and the dipole approximation can also be different, but the main point here is that you have this kind of one electron potential, and you want to use this to describe or to somehow simulate your system. Now, if you look at this, you may ask yourself, well, what is this potential? Where do I get this from? Now, for atoms, we kind of know what's relevant, and we can guess or come up with a sensible potential. But now, if you say you want to do it for a molecule, then of course it's a bit more of a challenge. And then what's also often the problem, or what is considered a problem in this kind of approach, is that you do not really include the many electron effects, at least not the time-dependent many electron effects. Now in this talk, I would like to show you a method which can actually do this, in principle at least, and this is the so-called exact electron factorization. And what happened here is that I replaced this potential which I had before now by a general time-dependent potential. And what I'm claiming, what I want to convince you of, is that this exact electron factorization is a method to map the many electron problem, in principle exactly, to a one electron problem. And it's a method which gives you immediately the equations to calculate this V of R and T, so to calculate the effective potential. And also one of the goals of this talk is to show you how this one electron potential looks like if we really have many electrons that we are describing. Now, the content of the presentation is first going to go through the idea of this exact electron factorization and some intuitive picture. I'm also quickly going to relate this to density functional theory and to this von Oppenheimer picture. You will see why. Then I'm talking a little bit about the peculiarities of the exact electron factorization, because it's a special theory and we have some interesting properties of the theory that might be surprising for you. Then I will show you an example of such a one electron potential of a many electron dynamics, and I will show you that it's pretty ugly. But I will also show you what's important there and how to make it pretty. And in the end, I'm also going to give you an idea of how we want to really use this ansatz, or this idea of this exact electron factorization to simulate a proper many electron dynamics. So, the exact electron factorization, what is it? And to explain you what it is, I've made this little picture here. So this is just should be the many electron time-dependent Schrödinger equation, where we have some external potential which is made by the nuclei, and we have some electron-electron interaction. And of course, we have some time dependence here because we want to have some laser field interaction. Now, this picture should be such a molecule. And here, these red stars should be two nuclei. And then we have the yellow stars, which are the 5 electrons. Now, it's not a very realistic system, but I think you get the idea. We're also working, as I'm always working now in the von Oppenheimer approximation, which means these nuclei are fixed, they're clamped nuclei. Yeah? And now the idea is that we write our many electron wave function as such a product. And this is a product of a one electron wave function and the product of an n-1 electron wave function, which describes the environment. So I'm coloring one of these electrons blue here. I'm saying this is the electron that I want to look at. And all the other electrons now constitute the environment for this one electron. And the chi is the wave function of this one electron, and the phi is the wave function of all the other electrons. Now, mathematically, we are doing this by this well-known way of writing a joint probability density as a product of a marginal and a conditional probability density. So what we're saying is we have this product. The many electron wave function is this one electron wave function times this n-1 electron wave function. And we're now requiring the absolute square of the one electron wave function to be the exact one electron density. So we're integrating over all but the coordinates of one electron. This means the square is the exact one electron density. Now, we don't know the phase. I'll come back to this later. But as long as we make our theory correct and we compute all the observables correctly, this will not be a problem, and we will have a phase also for this wave function. And then, via this ansatz in principle, we can just define the this wave function of the environment, so of the n-1 electrons. And in this case, it is a conditional probability. So the absolute square is a conditional probability density. The function itself is a conditional probability amplitude, which tells you the probability of where these n-1 electrons are given an electron is at a certain position. So it's really like a time parameter. So it's also like given my time is this, given my nuclei are there, given one electron is at a certain position, what do the other electrons do? Now, this is also why this is normalized with respect to all the other electrons, but there's one electron which is an additional parameter, and of course our usual time parameter. Now the important thing here is that if we do this, we will find that if our total wave function obeys a time-dependent Schrödinger equation, some Schrödinger equation, also the chi, so our one electron wave function, will obey a Schrödinger equation. And it's also in this case, it's really a one electron Schrödinger equation, and you can, in principle, get all sensible one electron observables of the many electron system by just solving this one electron Schrödinger equation. And all the other electrons essentially appear just as potentials in this one electron Schrödinger equation. Now, that's the equation. It's for one electron. And I've written explicitly these different contributions to this one electron potential. I'm not giving you the formulas here. I only want to show you some kind of intuitive picture of what they are. So the first one is the first contribution that our blue electron here feels is the external potential. That's the interaction with the nuclei or with the laser field. Yeah. Now there's a second contribution, and this is the energy of the n-1 electron system. Now in this case, it's a 4 electron system. And you can imagine now, if I move this blue electron along from here to there, then the configuration of the other 4 electrons can change. Yeah, it can be there can be an energetically better state. So in this sense, the energy of these 4 electrons also changes depending on where my blue electron is. And this is this part of the potential, VH. Then we also have another part, which we call the geometric potential for certain reasons. This is an additional potential which comes from the fact that there's some kind of rearrangement happening. So if I move along from here to there, at some point, these electrons will change or may change their position. And there's some additional energy needed to do this. And this is what the geometric potential essentially represents. And then we also have 2 gauge-dependent parts. The gauge will be explained in the next slide. And there's a vector potential here, which is essentially related to the relative motion of this one electron with respect to the other electrons. And then there is a scalar gauge-dependent part, which is in some sense related to the relative motion of this electron with respect to some external clock that gives you the time parameter. So these are the different contributions. And I told you that the last two, this vector potential and this gauge-dependent part, are gauge-dependent. Now, what is the gauge? Well, the gauge is exactly that we have not specified the phase of this one electron wave function. But of course, we need this. I mean, to calculate observables, in principle, we need this. But it's a gauge filter. So we can choose any phase because this product is, so the product does not depend on this phase. So if I add a phase factor here, there should be an I here, and an I here, because S is real valued. So if I add a phase factor here, and just the opposite of this phase factor over there, the product doesn't change. So this S is it's a free variable. All that changes is that we have to replace our gauge-dependent potential by a new potential which depends on the time derivative of the S, and the vector potential by a potential that where we add the gradient of the S. Otherwise, all equations in the theory stay the same. The important thing is also that we have to be careful to define all observables that we want to calculate. So the momentum or the kinetic energy, they have to be gauge invariant. So they have to be defined properly. Yeah, in this gauge, I mean, you're probably familiar with it. It's the same that you're having in electrodynamics. Now, from now on, or at least from 2 slides onwards, I will use the gauge where the vector potential is 0. That's not always possible. In general, in rotating systems, it's not. It can be Ferri phases. There's maybe something related to spin, all this kind of fancy stuff, which I'm not going to talk about. I don't know much about it at the moment. But just for you to know, in principle, this gate is not always possible, and the electric potential that I'm going to ignore from now on, in general, has to be taken into account. So now I hope that I've at least pictorially convinced you that there is this one electron Schrödinger equation with all these one electron potentials, which is in principle an exact one electron theory of the many electron problem, at least if we know these potentials. These potentials are given by the wave function of the environment. Now, one important point that I just want to make, because there is this, I colored this electron blue, so it looks like a special electron, no? But it's not. I mean, the electrons are indistinguishable because we start from a fully anti-symmetrized wave function. So there is no, there's, at least as long as we don't make any approximation, we do not break the anti-symmetry of the full problem. No. Now, I promised you to tell you something about the relation to density functional theory. And here it is. It's just one slide. The difference is, it's now a static picture. Difference is, so in density functional theory, you're having your one electron density, and you compute this as a sum over Concharm of the absolute square of Concharm orbitals, where these Concharm orbitals are different eigenfunctions of the Concharm potential. So here I'm in this dot, this dashed line is the external potential for some model. And this solid line here is the Concharm potential. Here you have the two states, and this gives you some density. Yeah? So this is now based on this fictitious Concharm system of non-interacting electrons. We have some efficient approximations, but you know we have in principle some unknown functional dependency of the energy on the density. Now in this exact electron factorization, what we're doing is different. This is actually the density that, or the wave function that corresponds to the density that we also get if we add these two. You know? But now, at least in the sort of, if we do not include any time, then the exact electron factorization will give you one potential. It's this potential here, and the density will correspond to the ground state of this potential. Yeah. So the good thing here is that we have explicitly non-functional dependencies, but also the interpretation is very different from what you're used to be, what you're used to. Just as a side remark, if you do not include time and do not care about the vector potentials and about this interpretation of conditional wave functions, there's also orbital free density functional theory, which is in principle based on the same potential, just using a different formalism. Now, one more remark, because I will leave this later, is that there is this relation to von Oppenheimer. Now, those of you who know the exact factorization know this already. So here we had the many electron wave function. This is product of one electron wave function and this conditional n-1 electron wave function. But formally, it's the same, like if we would say that we have a wave function which depends on nuclear and electronic coordinates. And we write this as a product of a wave function for the nuclei only, and one for the electrons, which conditionally depends on the position of the nuclei. And this is now the exact version of what you usually would do in the Born-Oppenheimer approximation, where you say you have a wave function of nuclei and electrons, which is a wave function of the nuclei only. And then you have a wave function of the electrons, where you have, which is for each different position of the nuclei. Now this correspondence, I will use it once later. It's just for you to know where it comes from. Now, of course, we are working in a very different regime because we're only working with electrons. It's all antisymmetric. And also what's important here is that our one electron and this n-1 electron environment, so excitations in these two parts are on the same energy scale, which is why we cannot do something like a Born-Oppenheimer approximation. It's not quite true. Sometimes we can do, but in general we cannot. So it's related, but it's also different. So now there are some of the peculiarities of the exact electron factorization that I want to show you, and that you will also see later when I'm going to show you this exact potential, this exact one electron potential for the many electron problem. Now the first peculiarity is that our potential can have steps. And this is known from density functional theory and also from time-dependent density functional theory. They also have steps. It's related to our steps, very closely related. And these kind of steps are somehow, at least they are somehow relevant for ionization. So, and I think I just wanted to quickly give you some insight into what causes this step in this potential. So now I'm having a system here where I have one nucleus here with charge +2, one nucleus here with charge +1, and we have two electrons, same spin, so the wave function is antisymmetric. Now our one electron potential for this system would be the sum of these three potentials. So the sum of the external potential, where we have our nucleus, one nucleus here, another nucleus there. Then we have our average system of this environment, and we have the geometric potential. Now, just to show you, so this geometric potential always happens, it's relevant whenever there is a change in the environment. You know? And down here you see the wave function of the environment. You have to imagine this as a one electron wave function, which is going in this direction. So this x2 is the coordinate of the one electron. And x1 is your conditional coordinate, so it's the position of the other electron. Depending on where it is, the wave function of this environment will look differently. So in this region, we're having a wave function which is localized on one side, on one nucleus, actually on the nucleus of charge +2. In this region, we have a different state where the other electron, the environment is localized on the nucleus of charge +1. And here it's going back to +2. Now, and there is some change in this wave function here, which makes this bump here. And there's also a pretty small bump there, which is because this change happens over a larger region. Now that's, but what I really want to point out here is this step feature. And this step feature is essentially this change of the energy of the environment, the change of the energy of this electron number 2 from this state to this state and then back. So I think maybe it's easier to explain it with this picture. Imagine you have imagine you have this one electron that you want to describe, and you say it's somewhere coming from the right, and it's somewhere localized at this position. Yeah, that's the nucleus of charge +1. Now the other electron will certainly be at the nucleus of charge +2. Yeah, so this electron feels an energy which corresponds to the energy of this kind of environment state. But now if we move this electron over there, the other electron will certainly not be in this region, it will be in the other region. Yeah. So we have this kind of more or less sudden change from this position to this position, which effectively changes the energy that this electron sees. Then if we move it out again, this electron will at some point fall back, and the energy that this electron sees will again be different. That's the reason or the origin of this step. And as I said, it's kind of related to ionization, because if you imagine one electron going out, this electron going out, then depending on what's happening in this region, some kind of rearrangement, the energy that this electron feels may be different. So there can be some steps happening in the potential. And there will be. I'll show you. There will be steps. The second peculiarity for this explanation, I'm using this correspondence to the Born-Oppenheimer case, because it's easier to show here in the Born-Oppenheimer case. In this case, we're looking at a model where we have two nuclei. This is a fixed nucleus. And here we have a moving nucleus and a moving electron. And the potential is such that it's symmetric, so there's a minimum here and there's an equal minimum over there. And now if you look at the Born-Oppenheimer state of this problem, for the nucleus, for this nucleus, essentially you will see some kind of double world potential, where the ground state is this plus plus state, and the first excited state is this plus minus state. And you have this kind of tunneling doublet. Now, if you do the exact factorization on that, you will see that each of these states of the total system corresponds to different potentials. So the blue potential is again the potential of the ground state. It looks like the von Oppenheimer potential. The wave function also looks like the von Oppenheimer potential wave function. But the first excited state, actually, it is never reaching zero. So there is no sign change here. Not really, except if you change the gauge. You can do that, but in general, there's no sign change if you want a continuous wave function. However, this potential will have a large spike at this region. So it will be the same potential like the ground state, it will just have a large spike. And now you can imagine the von Oppenheimer cases, if you have a very, very large spike, this all goes to zero, and you can just shift, you can just remove the spike, change the sign here, and then you get to the left picture. You know? Now, what I want you to take away from this is that for our exact electron factorization, there are two important points. The first one is that in principle, every state of this n-electron system corresponds to an individual potential for the one electron system. And also, when this one electron density becomes small, there can be a spike in the potential. It doesn't have to be, but there can be. And this spike is related to this fact that we cannot change, that our wave function actually never really becomes zero, so we do not have nodes. We cannot really change the sign of the wave function. Okay, so now let me show you the potential. And I told you it's ugly. Now it's for a very simple model. The model is just one atom. You have one nucleus, and you have two electrons. Again, it's important, these are same spin electrons. So you have an anti-symmetric wave function. And what I'm now going to show you is, or what I would like you to focus on is this green curve here. So on this top left, you see the logarithm of the density, so that you know where the electron actually is, the one electron density. Down here in green, you see the exact one electron potential for this two electron dynamics. And over there you see essentially this region, just a larger part of this region. And up here you will see a laser field. Now, so this is what I'm showing you now. And now if you go along the laser field, look at the green potential, you will see what's happening. So you're seeing this kind of spikes appearing here. And then you're also seeing this kind of drastic steps appearing. Yeah? So it's really not such a beautiful potential. And what you're also noticing is that there's some kind of time dependence going on here in this region. Now, first, this spikes and steps, the things that make this potential rather ugly. So these features also occur in time-dependent density functional theory. And the steps, in our case, actually, for the atom at least, they're only in the gauge-dependent part of the potential. And so far, we've just ignored them. So they're kind of, in some sense, they kind of indicate some kind of rearrangement in the core, which changes the density of your outgoing electron a little bit. But it's always at positions where there is a very small probability of finding the electron anyway. So we just ignored the steps so far. These spikes, they actually prevent the wave function from having a node. And the trick is that we just say, well, our wave function may have a node. It's just like, like what we usually expect. And then we just ignore the spikes. And this is the, I would say that the spikes and the steps are not so relevant, at least the steps outside this region, outside the core region. Now there's also, but what you might have also seen is that there is this time-dependent ionization barrier. So this is now the core region, and you have to, your electron is ionizing from here somewhere out. And this is just shown for one snapshot. And this is really this barrier is really drastically dependent on your laser field parameters. So especially on the central frequency. The higher the frequency, the less important or the less time dependent it is. But for low frequencies, there can be a very, very strong effect here. And this is, of course, something that you really have to include because if you want to describe tunnel ionization, for example, well, you have the barrier through which you're tunneling is very, very important. So you need to somehow include this effect. Now, getting rid of this spikes and steps, it's actually easy. So we can make the potential pretty. And we can do this by using this, what we call this time-independent conditional amplitude approximation. Approximation is just that we're not having any time dependence in our exact electron factorization potential. The only time dependence is in the laser field. And we can also have a time, and we also do not assume that dipole is time dependent, or some kind of effective dipole is time dependent. Now, the underlying idea here is that if you're moving your electron out, there will be some response of the other electrons. So there's, we're assuming that this potential that the electron sees when it moves out is independent of whether the laser field is there or not. And this is the essence of this approximation. It can be calculated, principle for molecules. It has no spikes, it has no steps. It's the red line here compared to the blue line, which is the exact case. The problem is that it does not have this time-dependent barrier, which we sometimes need. Now, when can we actually use this approximation? We looked at it for a model system. So this is what you're seeing here is the laser field parameters. So this is the laser field. You have some central frequency, omega, and you have some field strength here. And here's also the gamma parameter. And you see that this approximation works rather well if you have rather large frequencies, so pretty large frequencies actually. But if you go and also for small frequencies but very low field strengths, but for larger field strengths and small frequencies, it's rather bad. And what we've plotted here is actually the number of electronic states that you need, because this TK approximation is kind of the idea that you only need one bound state here in this region, and otherwise you're just doing some kind of a continuum propagation. Well, you can see here that especially if you're going into this region, this kind of very relevant experimental region, you need typically many bound states to describe this dynamics correctly. So you would need you cannot really get this time-dependent ionization barrier, which is related to these excitations of this parent ion. Yeah, so now that we've learned this, how can we simulate something based on this electron factorization? And yeah, that's the idea again. We want to simulate this somehow in a one electron picture, but we learned now that we in general need to describe this effective barrier here. And to describe this effective barrier, we would need quite some excitations in this bound state region. So our idea, which we're trying at the moment, is the following. We want to describe these two regions differently. So we want to have some kind of coupled dynamics, because we know in principle how to describe this core region time dependently with the many electrons in a reasonably good way.
2 minutes, Axel.
Yes, I'm almost done. Almost done. Thank you. So we would like to do this with some kind of a full electron code. Describe this. Then from this description of the core region, we want to get the potential in this region. And we want to match this with analytical form, with a kind of analytically known form of the exact electron factorization potential out there. And then our plan is to do one electron propagation on this potential, which we get in this way. And in this way, we would like to avoid the problem of describing both the bound states, and we want to essentially solve the problem of coupling these bound states together with this continuum propagation. Yeah, that's what's currently underway. We call this the multi-level approximation. And now to summarize, I hope that I've shown you that the many electron problem can exactly be mapped to a one electron problem, that this one electron potential is spiky and has a few steps, but we can comb it, we can also remove the steps. But we need to model these excitations of the parent ion for this exact electron factorization to be useful. And now in the future, we just want to implement this and test it a little bit. And then there are many, many open questions, like how do we treat quantum nuclei? How do we get a better feeling for the vector potential or the gauge-dependent part? Or how, for example, also related to yesterday's talk, how we can connect the theory to the reduced density matrix formalism. Yeah, and with this, I would like to stop, and I'm looking forward to your questions.
Okay, thank you, Axel, for the talk. So now we have a few minutes for questions. So please raise your hand if you have any questions. Okay, Eva, and then Graham. So Eva, let's start. You can ask your question.
Thank you very much for your nice talk. Can you hear me?
Yes, I can hear you. Mm-hmm.
So I was wondering, a technical question. I was wondering when your potentials have these spikes and steps, how challenging is it for your numerical approaches? So what do you use for spatial discretization and time propagations?
Yes, we're not doing this yet. So what I'm showing you in these potentials is actually we solve the full problem and we calculate the potentials.
Mm-hmm.
The numerical solution of a wave function on this potentials is really challenging because you really have to get the step height correctly because you really cannot allow it to be zero. So it's we haven't succeeded with this yet. Mm-hmm. So it's what we have tried is to remove the steps and the spikes and to make a propagation on this potential. But we cannot numerically do this propagation on the real potential. Yeah.
Mm-hmm. Okay, thank you.
Graham, your turn. We cannot hear you, Graham.
Can you hear me now?
Yes, now we can, kind of. Mm-hmm. No, we cannot.
Okay, so Graham, if you're not, maybe we can take the next question and then come back to you afterwards. So Akon or Akon Volkmann.
Yes. Thank you. And thank you for your talk. I just maybe have just a fundamental or stupid question. You asked or you said that your wave function is actually exact in terms of indistinguishability and antisymmetry. Mm-hmm. But if you could go back to slide number 8, maybe. There where you presented your exact electron factorization. Here we see that you can split off just a single factor. And now let's, for example, just figure that we had 2 electrons. So therefore, on one side of the equation, you would have kind of Slater determinant or an explicitly anticorrelated or antisymmetric wave function. And on the other side, you would just have a Hartree product with no antisymmetry at all. How is this, how can we solve this contradiction? I don't see it right now.
The left side is right, the right side is not. So we do not have a Hartree product. the anti-symmetry is there in the product. I mean, it's just so if for example, if we okay, it's really there in the product. You just write your full wave function down here. You just compute the 1 electron density, takes the square root, then you have the magnitude of chi.
Mm-hmm.
You choose your phase, and then you just say phi is psi over chi. Yeah. So the thing is, it's in the product, but it's only in the product. And that's the thing. So we do not have it in the ansatz itself, but only in this product. But formally, it's all there. It's just hidden. So we cannot. I mean, from the potential, you cannot. From this potential, for example, yeah, you cannot from the green one. You cannot see that it corresponds to an antisymmetric state of the full problem. Yeah.
Mm-hmm.
Okay.
Okay. Yeah. Thank you.
Graham, can you try again?
Can you hear me now?
Yes.
Yep.
Ah, good. Yeah, as always, don't know why that wasn't working. Okay. Yeah. So Axel, yes. Yeah, it's a very nice idea, actually. I like this. The one question I have is that so in the exact factorization, which I obviously know better from the usual nuclear electronic separation, you end up that the coupling potential, the gauge potential, has the sort of the 1 over the density term affecting the electrons, which leads to the sort of problems where the density of the nuclei go to 0 for the electronic wave function. Yeah. Do you have sort of similar problems? Is this what's giving you the spikes? Because wherever you get a node in the probability for your many electron part, you're going to get a spike in the potential?
Yeah, of course. I mean, you can write all the terms essentially. So all the terms of the potential is something divided by the density.
Yeah, yeah.
By the 1 electron density, and whenever the 1 electron density becomes 0, you get something large. That's correct. But the difference, I mean, so for bound states, typically this 1 electron density is not really. I mean, it can happen. Yeah, it can happen that you have some spikes, or at least some. It's not so sharp features in this case, because the thing is if you have a true spike, you can just ignore it and just say you change the phasor. So you just you remove the spike. The only difference is that your wave function then can go through 0 and change sign, and you can just ignore it. Right? Sharp spikes are no problem. The problem is spikes which are not really sharp, so which are there but which are not so sharp, and then you have a problem. Otherwise, we just remove the spikes. Yeah. But it's different because we do not solve the problem. We don't want to solve it in a coupled way, at least not in the same way like it's done in the electronuclear case.
Okay. Yeah. Because you just take that more as an average potential that it's working in. Yeah. Yeah. Okay. Thank you.
Okay, Elke, can you just make it super short so we have like a minute and then we move on?
Well, exactly the slide that you're showing there, and you have the idea that you are building your, let's say, effective potential for the, let's say, core or atom region, and then you plug the analytical function that you get from the pulse, if I understood you correctly. But what are you planning to do with the interface region between the two? Because either you would have to go very big with the description of your core part, or you will have an interface region where you don't really know, or where you will get inaccurate with your description.
Yes, yeah, I mean, sure. So the thing is, I mean, for the initial potential we can get, we can get initial potentials just by taking tricks, but we haven't done it yet.
Okay.
in 3D. I mean, I've done it for DFT and this kind of you can just by if you know the density, the electron density reasonably accurately, you can get the initial potential. The asymptotic region is a bit tricky. You have to be careful there, but in principle it can be done. And then the idea is really just to change this part. Of course, you have to get a reasonably good get a reasonably good description up to this asymptotic part, but it's not so large. At least it looks not so large so far. But I mean, we're testing. We're starting to test this. So okay. I can tell you more maybe next time.
Okay, thank you.
Okay, thank you, Axel, for the talk and the question session. So I think we'll move to the next speaker. Thanks, Axel.
Thank you very much.
So Vincent, you're here?
Yeah, yeah. Can you hear me?
Can you share your? Yeah, we can see you and hear you. Can you share your screen?
Yeah,
Please?
okay. I'm sharing my screen now. Can you see my presentation?
Perfect. Okay, so the
Okay.
next speaker is Vincent from Madrid, and he will present the XChem code and some application to it. So please.
Okay, perfect. So please let me know if you can't hear me. Okay, so I will start. First of all, I would like to thank the organizing committee for giving me the opportunity to be here talking. As you can see in the title, I will be talking about the XChem code and the new implementation to compute photoelectron angular distributions. So why to include photoelectron angular distributions in our code? But well, nowadays, in some experiments, it is possible to detect the direction of ejection of the photoelectron during ionization. As an example, we see here a rabbit experiment published in Science in 2018 for carbon monoxide molecule, and they are able to distinguish the angle between the molecular axis and the laser polarization axis. At the same time, they are able to detect the direction of ejection of the photoelectron. So if you want to describe that theoretically, you need to include photoelectron angular distributions in your code. So that's why we wanted to include them in our code. Sorry. So here is the outline of the talk. First of all, I will be talking about the XChem code, the theory behind the code, and I will also show briefly some of the results the XChem code has produced. Then I will move to talk about the new implementation that includes photoelectron angular distributions, and I will show the results I obtained with the carbon monoxide, still unpublished, and also the results of the pyrazine that a colleague of mine, Pedro, has obtained too. So I will start with the XChem code. Sorry. Here you can see the people who started with the XChem code around 5 years ago. At that time, all of them were in the University Autónoma of Madrid, but as you can see, some of them has moved. Fernando Martín and Jesus González are my PhD supervisors. And at the end of 2018, I did an internship in the University of Central Florida with the supervision of Luca Argenti. So as you can imagine, my PhD thesis is very related to the XChem code. Also, something can interest you is that soon the XChem code will be open source. So probably you would like to test it and to do some calculations. The XChem code is able to describe single ionization. And for describing photoionization in molecules, you need to be able to describe bound state and continuum state. For describing bound state, Gaussian basis functions have shown that are appropriate. They have been used during decades, and they are implemented in most of quantum chemistry packages because computing the electronic integrals between Gaussians defined at different centers is fast. The problem with Gaussians is that when you try to reproduce the oscillatory behavior of the photoelectron in the continuum, they build up a lot of linear dependencies. In contrast, B-splines, they are really good for describing this oscillatory behavior. They also produce sparse matrices, but the problem, if you try to describe bound states with B-splines, is that for the computation of the electronic integrals of B-splines defined at different centers are very expensive. So what the XChem code does is to benefit from both of them and construct what we call a GAPS hybrid basis. That is a Gaussian and B-spline basis. This GAPS basis is constructed with polycentric Gaussians centered at the atomic positions, as you can see in this schema. We also have monocentric Gaussians centered at the center of mass of the molecule. And these monocentric Gaussians overlap with the polycentric Gaussians and go a little bit further. On top of that, we put B-splines starting at some point, what we call R0. And the key point here is that the polycentric Gaussians touch the B-splines, but the polycentric Gaussians don't overlap, don't touch with the B-splines. So we can neglect the integrals between polycentric Gaussians and B-splines. Here, you can see the performance of the GAPS basis for scattering state of the hydrogen atom. And you can see how the gas basis agrees really well with the analytical function. So depending on the integrals computed in the ISCHEM code, we can differentiate two parts. We have the quantum chemistry part that computes all the integrals between Gaussians, and the scattering part when the B-splines are included. So now I'm going to pass to describe these two parts. First of all, the quantum chemistry part. In the ISCHEM code, there are different types of orbitals. We have polycentric orbitals. These orbitals are obtained at a CF level. You can, and the ISCHEM code reads these all orbitals as an input. You can use any program you wanted, but then you have to transform the orbitals to the Molkas format. That is the format the ISCHEM code reads right now. Also, we have monocentric Gaussian orbitals. These monocentric Gaussian orbitals are created with an even-tempered basis set of monocentric Gaussian functions centered at the center of mass of the molecule. As I said, it's an even-tempered basis set that is defined by a geometric progression. You can see here that these basis functions are defined with R up to 2k plus L. So we have these two different values that we have to play with them when trying to do calculations. For instance, if we increase the k value, we will increase our radial extension. The monocentric Gaussian will arrive further. And if we increase L, we will increase the angular flexibility. So imagine we have a big system and the polycentric Gaussian is a little bit far from the center of mass. We will have to increase we will have to put the B-splines a little bit further. And to be sure that the B-splines and the monocentric Gaussians are touching, we will have to increase the k value to increase the radial extension. Also, we have different kinds of states. We have source state that are the states computed with polycentric Gaussians. The typical source state are the ground state or excited states you wanted to include in the calculation. We also have the ionic state that are the parent ions included in the calculation. These parent ions are described as a linear combination of configuration state functions with a defined spin. And with a Guga table obtained by Molkas, we transform them to linear combination of Slater determinants. So we can augment on every possible orbital. So we augment on each parent ion on every possible orbital, polycentric orbital and monocentric Gaussians. And then we transform back from Slater determinants to configuration state functions with another Guga table obtained by Molkas. So at the end of the day, what we have at the end of the quantum chemistry part is all the 1 and 2 electron operators between all these states. The typical operators is overlap, Hamiltonian, dipoles, and whatever. So now in the scattering part, the first thing the scattering part does is to compute the missing integrals, that are the integrals between Gaussians and B-splines and between B-splines. Between the closed clapping approximation, the scattering states are created with the source states that are the ones defined with polycentric Gaussians and the augmented states. States augmented either in a monocentric Gaussian or in a B-spline. Here you can see the schema of a typical matrix in the scattering part of the ISCHEM code. It could be the overlap, the Hamiltonian, or other operator. You can see here that all the integrals computed between Gaussians are computed in the quantum chemistry part. I forgot to say that before, but the integrals we obtained it from Molkas. It's Molkas who is computing the integrals, and we obtained it from there. And we can see also here that the integrals between polycentric Gaussians and between B-splines are neglected, are 0. We also see here the interference region between monocentric Gaussians and B-splines. So these integrals are computed. And we see also here that when we just have B-splines, we obtain a sparse structure. So now there are two ways to proceed. We can use fixed boundary conditions by imposing the wave function to be 0 at the end of the box, and for example, by neglecting the last B-spline. And if we diagonalize the Hamiltonian, we will obtain a discrete spectrum. And if we transform the different operators to the eigenstates of this Hamiltonian, we will have different matrices that are useful for propagate. So we can do time-dependent propagation with these matrices. We include a complex absorbing potential. So during the propagation, when the photoelectron is arriving to the end of the box, it is absorbed, so we don't have reboundings. Also, we also have the scattering stage. There are several ways to compute the scattering stage. The most standard one right now is to compute them after the box eigenstate, and the scattering stage will be defined as a linear combination of different box eigenstates. So the scattering stage, we can compute them as at the desired energies, and we also obtain the transition dipole amplitudes. So with that, we can calculate the cross section, either in velocity or in length gauge. Sorry. Okay. So now we have an idea of how the HChem code works. Now I'm going to briefly show some of the results the HChem code has produced in the last years. Marcus was focused mainly on the nitrogen molecule you see here, and among other things he did on nitrogen, I'm showing here just some of the results he obtained. In his calculation, he considered 3 different parent ions, and what I'm showing here is the cross-section between the second and the third threshold that is full of Rydberg states, as you can see here, that is known as the Hopfield series, and we can see how the cross-section obtained with this chem really agrees with the experimental data obtained by synchrotron radiation. Something similar was done by Sonia with the oxygen, and what we see here is the cross-section for the continuum of this pi G parent ion, and we see how the code is able to reproduce what is observed experimentally, especially in the presence of resonances. We see that the cross-section agrees with experimental data, and we see here also here that the tendency is also well reproduced. Now I'm showing the results produced by Leon in the neon atom. It was the first time we considered excitation between continuum states with the HChem code. So what he did was to reproduce a rabbit experiment doing time-dependent propagation with the information obtained by the HChem code. And in the experiment, they were exploring an energy region where there were different resonances. So in this complex area, the HChem code was able to reproduce something very sensitive as the atomic phase for these 2 sidebands. And as you can see here, the agreement between the HChem code and the results and the experimental data is almost perfect. The HChem result is the black line you see here. So you can see how the HChem code is able to reproduce something very sensitive as the atomic phase. So we have seen how the HChem code is able to reproduce different experiments, what the HChem code is able to do. So we wanted to go one step further, and we wanted to include the photoelectron angular distributions. So that was done during my internship in the University of Central Florida with the supervision of Luca Argenti, among other things we did. So we implemented the beta symmetry parameter and the molecular frame photoelectron angular distributions. So what is the beta symmetry parameter? Well, imagine we are in the laboratory frame and we know the direction of the laser polarization axis, and we have our molecules randomly orientated. If we can detect the direction of ejection of the photoelectron, we can express the cross-section depending on this angle theta. And you can see here the beta. So if the beta tends to 2, it means that the preferred direction of ejection is almost parallel to the laser polarization axis. But if the beta tends to -1, the preferred direction is almost perpendicular. I have to mention that the beta is always between -1 and 2 by definition. In contrast, the molecular frame photoelectron angular distribution, as the name says, it's in the molecular frame. So here, what we obtain is the direction of ejection of the photoelectron in respect to the molecule. So now I'm going to pass to show the results I obtained for the carbon monoxide that are still unpublished. Why we chose carbon monoxide? But well, carbon monoxide is an heteronuclear molecule, so we expect to have a rich angular distribution. Also, the phase-back resonances in carbon monoxide hasn't been widely investigated yet, so we wanted to do it. And also, if you remember in the first slide, I was talking about a rabbit experiment that they were able to detect this direction of photoejection of the photoelectron. And that was done with carbon monoxide. So because of this reason, we chose to do it with carbon monoxide. So here you can see the parameters I used in the HCM calculation that I'm going to show here the results. We did different calculations, but we observed that at L equal 4, we reached convergence. So as you can see here, I'm using a very big RAS, and we are including 3 different parent ions in the calculation. In fact, 4 because the pi is degenerate. Here you can see from where the electron is leaving to form these parent ions. I have to mention that that is just an approximation, a molecular orbital diagram with chemists like to represent, but in fact, our wave function is multi-configuration, it has more than one Slater determinant. But you can see here that for the ground state, we have even more than 11 millions of Slater determinants. You can see here that the ionization energies obtained with the HChem code are the ones you see here, compared with the experimental ones are quite close. So with this RAS, we are able to reproduce well these ionization transitions. And regarding the B-splines, we put the first B-spline at 8.7 atomic units, and our box is of 200 atomic units. So now I'm showing here the cross-section obtained with the HChem code with this calculation in the energy region where there are experimental data. We are showing it in the velocity and in length gauge. We can see how we are able to describe the tendency. The match is not perfect. We also have to have in mind that the HChem code is working better close to the thresholds when the kinetic energy of the photoelectron is low. In any case, describing this cross-section in this energy region is very difficult. As an example, I will show the results of different theoretical methods for the continuum of the first sigma, the first threshold. So you can see here how the other methods are also in the same, trying to describe the experimental data almost in the same tendency as the HChem code, but any of them is matching perfectly the experimental data because it is really difficult. So we want to focus in the presence of resonances. Also, you see here that the HChem code is the only method who is reproducing these resonances here. And we want to focus in this area. So here you can see the cross-section in this region. You see here how the gauge invariance is quite good. And for the first threshold, we observe that there are a lot of resonances, and the same for the second threshold. That's the red line is the continuum of the first sigma parent ion, and the green line is the continuum of the pi parent ion. So what we observe is that there are several resonances, and as we will see in next slides, these resonances are going to change the photoelectron angular distributions. Now I'm showing the beta symmetry parameter the same way as before in the energy region where there are experimental data. We see how our results match the experimental data, especially in the first and the second threshold, the red and the blue line. We also observe that the gauge invariance is also quite good. And what we also observe is that in the presence of resonances, the beta symmetry parameter is changing abruptly. If we focus in this region, we see what we were saying, that the resonances are changing the preferred direction of ejection of the photoelectron. For example, if you remember what we said before, when the beta was close to 2, the preferred direction was almost parallel to the laser polarization axis. And when it was close to 0, all the directions will have the same probability almost. So we see how resonances are changing this. For comparing the molecular frame photoelectron angular distributions, we compared our results with this reference. We have to thank here Robert Lucchese, who sent us the information of this paper to compare directly with our results. in this experiment they were reproducing, they were able to detect the direction of the molecular axis in respect to the laser polarization axis, but they were not able to know if the carbon was on one side or the other side. So that's why we have a plane of symmetry in that direction. So what we are seeing here is the angle between the direction of ejection of the photoelectron and the angle between the laser polarization axis. And we can see different things. On one hand, we see that the Isken code has a very good gauge invariance. The velocity and length gauge results are almost identical. We also see how our results are really close to the results obtained in this paper by Lucchese. And the method they were using is multi-channel swinger configuration interaction method. That is a really accurate method. So we can say that the Isken code is able to reproduce the same results as this method. That is really accurate. And we also see how the MF patch, the direction of the photoelectron, is changing with the kinetic energy of the photoelectron. Something similar we have when we consider the direction of polarization parallel to the molecular axis. As you can see, we have almost the same conclusions as in the last slide. Here we can see a little bit more differences, but these differences are when the kinetic energy of the electron is low. That's the part when the Isken code is working better. So probably we can have here some discrepancies, but as you can see, they are minimal, and the tendency is almost the same in both calculations. So now I wanted to show the MF patch in another way. Here in this schema, we see what we are seeing in the plots. We are just considering this plane, and we are varying this angle theta. The angle theta we see here is this angle theta in the plots. So we are seeing how the preferred direction of ejection of the photoelectron is varying with the energy. For the case of the laser polarization perpendicular to the molecular axis. To guide the eye, I put here the partial cross-section, and we see that in the non-resonant part, for the continuum of the first sigma state, sigma parent ion, we see that the preferred direction is almost parallel to the direction of the laser field, the laser polarization axis. But in the presence of resonances, this is completely changed. And it is not changed always the same way. Depending on the resonance, the direction of photoelectron will change. It could go towards the oxygen side, or it could go towards the oxygen side. That depends. Something similar we can see in the continuum of the pi parent ion. Here, the preferred direction is also parallel to the laser polarization axis, but we can see also a little bit of contribution in the carbon side and in the oxygen side. And we also see how resonances are changing this preferred direction. For example, in this resonance, the preferred direction is going towards the oxygen. Here, I'm showing something very similar, but now with the laser polarization axis parallel to the molecular axis. Here, we see, in the case of the sigma parent ion, that the preferred direction in the non-resonant part is almost towards the carbon, but the presence of resonances are again changing everything. For example, in this resonance, the preferred direction is moving towards the oxygen. It is very clear here. In the continuum of the pi parent ion, we have two preferred directions that are 45 degrees and 135 degrees, and also resonances are changing the preferred direction. So I'm going to show a movie of that I think is very illustrative. Okay, we'll put that here. So what we are seeing here is the same as before. For the case of the laser polarization axis parallel to the molecule, here we have the carbon, and here we have the oxygen. And we are going to see how varying the energy, the MF path is changing. And we said before, in the non-resonant part, here, the preferred direction is towards the oxygen, towards the carbon. And we will see what happens. We see how it's changing. And in the top of that peak, in the top of the resonance, the preferred direction has moved towards the oxygen. So now I will just put the video and you will see how it's changing with the energy. When we will arrive to this area that is full of resonances, we will see how the MF path is changing very, very fast. Okay? So we see how every time we reach a resonance, the photoelectron angular distribution is changing. So you see here how it changes very, very fast because it's full of resonances. And when there are no resonances, it changes very softly. So we see every time how every time we reach a resonance, the MF path is changing. Okay, I think we have enough. We'll stop it. So we wanted to understand what this change when we reach a resonance was happening, and we focused on this resonance, where we know that in the non-resonant part, the preferred direction is towards the carbon, but in the presence of the resonance, the preferred direction moves towards the oxygen. So to try to understand what was happening here, we compute for the non-resonant part the Dyson orbital between the ground state and the parent ion. The Dyson orbital tells us the information from where the photoelectron is leaving the system. So we see that the photoelectron is leaving the system mostly in the carbon side. So that could explain that why in the non-resonant part, the preferred direction is towards the carbon. For understand what was happening in the resonant part, we have to have in mind that a resonance is created by a metastable state embedded in the continuum. So we investigated this metastable state, and this metastable state was the pi parent ion with an electron in a very diffuse Rydberg orbital we see here. And we see here how this Rydberg orbital is a little bit towards the oxygen. I don't know if you can appreciate it, but it is a little bit towards the oxygen. So that could explain that why in the presence of the resonance, the preferred direction is towards the oxygen. So now I'm going to pass to describe briefly some of the results my colleague Pedro has produced with the pyrazine molecule. These results are still also unpublished. He has produced too many results, but I'm just showing some of them because of the time. So here you see the pyrazine molecule, and here I'm showing the cross-section of the pyrazine for the direction of polarization of X direction. And we see how we are able to see different resonances. So the thing is, in the pyrazine, everything is more complicated. We have a lot of parent ions. In this here, we are showing just 4 parent ions, but in the calculation, we are including 5 parent ions. So we see how there are a lot of resonances, and we are just showing one direction. In the other direction, we have other things even more complicated. And we also compute the beta symmetry parameter, and we see here that also the presence of resonances is changing abruptly the angular distribution. We also see how the gauge invariance is quite good, and just it. We also compute different, Pedro computed different molecular frame photoelectron angular distributions, and we are going to focus first in this peak. In this peak, in this energy, we just have 2 different parent ions opened, these 2 thresholds. So we are showing here this the angular distribution, and we see how it's really complex because of the molecule, because of the complexity of the molecule. I also have to say that this calculation is for L equal 9. And we also investigated this peak, you see here, the one next to it, and we see something similar. The photoelectron angular distribution are very complex. So that's just a little bit of what Pedro did for the pyrazine. So now I'm going to pass to give some conclusions and future perspective. So we have seen how the ISCHEM code works, and how the scheme code is able to reproduce different experimental data. Also, remember you that the scheme code will be open source very soon, so probably you would like to use it. And we have implemented photoelectron angular distributions. We have compared our MF patch with the one of this reference, and we have seen that they are as good as this multi-channel swinger configuration interaction method. And we also have shown the results of carbon monoxide and pyrazine, and we have seen how the presence of fastback resonances are modifying this MF patch. For the near future, we would like to do time-dependent propagations. I say near future, but we are going to do it right now. We have everything prepared to start doing that. We would like to, for example, simulate rabbit experiments and to propagate the photoelectron wave packet to the scattering state and to follow the photoelectron angular distributions. So to the end, I would like to thank all the people who started with the scheme code, especially my PhD supervisors, Fernando and Jesus, and Luca Argenti for the nice time I spent with him in the University of Central Florida. Also, I would like to thank Marcus, Sonia, Leon, and Pedro for the results I've been showing in this presentation. And also, I would like to thank Robert Lucchese for sending us the information to compare directly our results with his results. And also, I would like to thank you for your attention. I'm open to any question you have.
Okay, thank you for the presentation. Elke was first, so Elke, please.
Thank you for the very nice talk. If you consider, well, of course, you first have to do your mole cost calculation as far as I understand, but as soon as you have that, how computationally demanding are your simulations compared to the initial mole cost simulation?
Okay, I will answer the question without showing my slides because I don't know what happened, but you can hear me?
Yes.
Okay, perfect. So it depends on the system, and it depends on the size of the RAS. If you have a big RAS, it will be slower. It also depends a lot on the angular momentum. If you want to have a lot of angular momentum, you will have to compute a lot of integrals. So it depends. I could say that for the carbon monoxide I was showing with L equal 4, I would say that in less than 1 week you can have all the calculation done with 10 nodes and with 16 processors node.
But the time determining step, the rate determining step, is then the mole cost calculation, or is it your simulation?
Sorry, can you repeat the question?
Well, you have two parts. You have the mole cost calculation and you have your simulation.
Yeah.
Which one is more demanding?
So it depends. It depends. Like if you imagine you want to have a really big box, you want to imagine a box of 1,000 atomic units. In that case, it will be more expensive, the scattering part of the code that has to diagonalize all the Hamiltonian with all the B-splines. And so it completely depends on the system.
Okay.
In another way, if you have a big molecule that with a really big RAS and you have a small box, it will be the opposite. It will be more expensive, the quantum chemistry part, than the scattering part. So it completely depends on the molecule.
Okay, thank you.
Okay, next question, Gilbert Grell.
Okay.
Okay, I hope you can hear me. Yeah, thank
Yes.
you for the nice talk. I was just wondering, you showed the cross sections for oxygen and I think also for CO, and you mentioned that it's difficult kind of to describe the cross section in this medium energy region just over the resonances.
Yeah.
And in fact, there you had some like some more pronounced disagreement maybe with experimental data. I think it was more visible in the oxygen case actually. And
the oxygen
I
case.
was wondering why this is the case, because I would, like, frankly, naively, I would expect that a code like XChem that is very
Okay, So
very good. Basically, yeah, here you can see it, right? The discrepancy, like just after the resonances stops, the cross sections are just lower than the experimental data, and then later on, so starting from 27 eV, it catches up again. So
the thing is, like, the ISCEM code is really taking into account a lot of electron correlation. So when the photoelectron is leaving with a low kinetic energy, the ISCEM code is really well reproducing this situation. But as I said, we are using a gaps basis. So we have a part where we just have a Gaussian. So the Gaussians have to describe a little bit the Gaussian, then overlap with the B-spline. So when we have a high kinetic energy of the photoelectron, the Gaussians can have a little bit of problems to reproducing these fast oscillations. So that's why when the kinetic energy of the photoelectron is a little bit high, we have a little bit worse results. Do you understand what I mean? Sorry, can you hear me?
Oh, I think we lost, I don't see him in the list of participants, so.
Oh.
Okay, so maybe you can continue the discussion during the middle speaker session.
Okay.
I have just two short questions, maybe.
Yeah.
Maybe I missed it, but do you compute the two electron integrals between the B-spline and the Gaussians, or it's only the one electron integral?
No, just one electron integral. It is here, yeah. No, we just compute one electron integral between monocentric Gaussian and B-splines. We only have one electron in the B-splines and in the monocentric Gaussians.
I see. Okay. And you said that the code is going open source, so I guess it relies on Molcast. But are there other libraries? What language do you? I mean, it's a Python, Fortran, C, whatever. Just give us some technical.
Sorry, you asked for the open source, when it will be?
No. What it relies on. So what kind of libraries we would need if we want to use it? Is it just Molcast and your code, and it's a self-consistent code, or?
Yeah, the Open Molcast is open source already, so you can also use it. So you won't need anything. You also need Overcode and Open Molcast, and with that you just have to install it and to use it. And it will be soon. We still don't know when, because we are doing the paperwork right now. But yes.
Okay, it's written in which language?
In Fortran, but it has an interface with Python 3 right now.
Okay.
It is. I also haven't said it, but the ISCEM code is very user friendly. The input files are really similar to the input files of Molcast, so it is really easy to use. If you are used to use quantum chemistry packages, it is really easy to use the ISCEM code.
Okay, thank you. Jesus, if you have really short question or comments?
Just referring to this, the libraries that we are using are just the standard MKL or LAPACK or SCALAPACK. Right? So it's nothing fancy. And
great.
Also these libraries for the Molcast code, so in principle it's fine. Okay,
great. Okay, thank you very much. So, thanks again, Vincent, for the nice talk. And we'll move to the last speaker for this morning. I see him now on the list. So it's Carl Michael Sims. I hope I didn't mess up his name. Carl, are you? Can you hear me?
Thank you.
Yeah. Okay. So can you share your? Yeah, perfect. Okay. So we're all almost in time. And well, I won't read the title. I guess you can start now.
Okay. Well, thank you for the introduction, and thank you to the organizers for giving me the chance to speak here. My name is Carl Michael Sims. I'm a PhD student in the group of Stephanie Greff in Jena, and the title says I'm going to talk about quantum mechanical simulations of attosecond XUV ionization dynamics using atomic and molecular model systems. And I just want to start with a very brief recall from what we probably all know. What happens if we ionize a hydrogen atom or any simple system in a single active electron picture? what happens, like we have our XUV pulse and we have our ground state here. And if the energy provided by the XUV pulse is larger than the ionization potential, we will create a photoelectron in the continuum with the energy given by this formula, called the photoelectric effect or reflection principle, however you like. And I refer to this now as a long pulse limit, when you really have a long XUV pulse with a very short and well-defined spectral width. So the first question is, how accurate is this picture if we then go into attosecond pulses, because that's obviously what you want to do, as my title suggests. And well, you can literature or just make a little calculation, and you will see, for example, if you look at the photoelectron spectrum for like a hydrogen-like atom, where we indicate again the one photon limit here with a dashed line, you will see two effects. First of all, if you decrease the pulse length, the very obvious effect is that the intensity decreases because the energy brought in the system is less. But what happens as well for attosecond pulses is that you shift your photoelectron spectrum away from the expected one photon dashed line towards low energies. And well, in the attosecond regime, this can be explained using this very simple picture to decompose our photoelectron spectrum in a transition dipole moment and the spectral intensity, like we know, for example, from SFA. And we know then for long pulses, like for 5 femtosecond pulses, we have a very well-defined spectral intensity around this dashed line with a almost not varying transition dipole moment, which gives the spectrum then. And if we then slowly go into the attosecond regime and our pulse gets very broad in the spectral representation, what will happen ultimately is that it's so broad that it basically more or less constant ranges over the energy range, and then our spectrum shifts more or less towards the transition dipole moment regime towards low energies. So that's more or less a little introduction to our attosecond XUV ionization in like 1 electron systems. And of course, we want to go beyond 1 electron in a system. And in the literature, you can find a plethora of very interesting work on that, on many electron atoms. And I'm just going to reference 2 here. For example, the work from Michael Ivanov on helium atom and its attosecond dynamics governed by electron-electron correlation. So what they showed is here the parent ion dynamics of the coherent wave packet. And what they discriminate are 2 timescales. So the so-called timescale, the instantaneous timescale during the XUV absorption, which they refer to as shake up and shake down processes. So this is the excitation. This is the excitation of excited states beyond the ground state in the parent ion, which you see here, for example, in state 2 and state 4, which are excited during the XUV pulse interaction and which obey the symmetry of the initial molecular atomic system. But you can also see, for example, state 5, that there is dynamics happening long after the pulse is gone. And they refer to this as knock-up and knock-down processes. I introduced this here rather thoroughly because this is a language I'm going to use later as well. And of course, very famously is this work, attosecond correlation dynamics paper, where they use the streaking technology to extract time delays and to characterize shake processes, so instantaneous processes, as shown here, experimental and theoretical work. Okay, so we've seen that in the literature, for atomic system, there's quite a lot of work around, also for not just 1 single active electron, but also 2 and many body electron systems. And in general, shake up down processes are well known, knock up processes, then Auger effects, as you heard yesterday, and of course, very famously, ionization time delays, such as Wigner time delay, Coulomb, and streaking. So the question which arises now, in which my talk is considering, is what about molecules? So if we now go to multi-centered systems, to our molecules, how well do these properties we find in atoms hold for molecules? what kind of effects arises because we have now differently bound electrons in strength and location, and what's the role of electron-nuclear correlation additionally to the electron correlation effects we know from atoms, and can we somehow control post-ionization dynamics? This is a rather long list. I'm obviously not going to address this all, but I'm trying to introduce to you the model system we are using in quite thorough details. It's a numerical based conference, and I'm going to briefly explain the attosecond dynamics we see in this model system. Okay, so the molecular model system we are using is the extended geometric molecular model system. We actually heard of it very briefly yesterday as well, and it's shown here in this little picture. And I just want to stress in the beginning, this model system is designed to mimic differently bound valence electrons in arbitrary molecules. It's not here to, it's not meant to mimic a specific molecule. It's just in general to try to get general applicable insight into ionization processes in molecules. And for this, I said we use this model system, and it's comprised of 5 particles. And they are all in a 1D real space. So all we are talking about is basically one dimension in real space. And we have these 5 particles on there, on this one-dimensional world. And the outer nuclei here and here, they are fixed. They don't move. They just come up in our Coulomb potential. And the 3 inner particles are described quantum mechanically exact. And they are obviously about to move in their respective one dimension. So we have this time-independent Hamiltonian describing this model system. And as said, we have 2 electronic and 2 nuclear degrees of freedom, each in 1D real space. On the right-hand side, you can see the corresponding potential. And since we are in 1D real space, we need to describe ionization, meaning to leave the parent ion. We obviously need soft or truncated Coulomb potential to allow for actual ionization process. That's shown here with arrow functions. And then we have parts for the nuclear repulsion. And between the outer and the center nuclei, we have electron-nuclear interaction terms, and we have the electron-electron interaction term. What we can do, and what we do to kind of create an analogous picture known especially in the quantum chemistry world with potential energy surfaces, we create our initial wave function, our initial 3D wave function, by first of all obtaining adiabatic electronic eigenstates by solving this time-independent Schrödinger equation in 2 dimensions, relaxation methods, so 2 dimensions the electrons, and treating the nuclei parametric just for the initial wave function, just to have the concept of potential energy surfaces. If we do this, the potential energy surfaces are shown here. And then to have our initial 3D wave function, we just multiply our ground state adiabatic electronic eigenstate with a Gaussian to fit and to mimic the nuclear part of our 3D wave function. Okay, this is our model system we are using for the initial molecule. Now, obviously, if we ionize this model system, one electron will leave the system, and we have a parent ion system, which then has 1 electron less, and then it's described with 1 less electronic degree of freedom, with the here shown Hamiltonian and potential. And for this, again, we can solve it. We can solve the time-independent Schrödinger equation and obtain potential energy surfaces for our 1 electron parent ion. And now it's important to point out that this obviously is not a quantum mechanical exact comic of what's happening in the parent ion, because the electron can be on the left-hand side, that would be its ground state, but it can obviously also be on the right-hand side. So basically, this is the smallest model of a hole or electron migration, however you want to call it, or charge transfer. And we can see this if we look here at the adiabatic 1 electron eigenstates, and we look at the squared modulus of the wave function corresponding to these states. we see that in the ground, in first excited state of the parent ion, the electron is located on the left-hand side, whereas for NS2, we had a charge transfer to the right-hand side. Okay, last but not least, we need a laser to have we need an XUV laser to have our ionization process. And we do this by a very short attosecond pulse in velocity gauge and using the Dipole approximation. And then, as said, we initialize our system. We have our very, very spectral broad pulse, which basically is able to excite all kind of one electron and also double ionization states. And then we have our real-time propagation using the three-dimensional time-dependent Schrödinger equation, split operator on a grid, using the here shown parameters. Okay, this was in broad detail how our model system works. Now let's have a look at what's happening when we propagate our time-dependent Hamiltonian with the attosecond XUV laser pulse. And we first start by looking at what's happening to the electrons upon ionization. And for this, I show you here on the right-hand side the density when we integrate out the nuclear degree of freedom. So we see where our two electrons are. And here we see what's already mentioned quite a few times, the recent talks, that electrons are indistinguishable. So we see that the X electron can be at negative values, meaning on the left-hand side of our molecule, and the Y electron at the same time on the right-hand side. So here, but also vice versa, X can be at positive values on the right-hand side, while Y is at negative values on the left-hand side. Just shows us the indistinguishability of electrons. Okay, so now let's our laser interact, and we see at 1, 2, and 3 femtoseconds, we see how the electron density evolves. And I want just very briefly qualitatively discuss this here because it's just nice visual picture. Because what we see here is that, well, most of our two electrons stay bound, but there is a good portion of it where we see that one electron coordinate, for example, X, we see the electron moving towards higher position values, so it gets ionized and emitted out of the system, whereas the Y electron stays around ±5, so in the parent ion. And we have this in X, forward, backward, and we have the same in Y direction, forward, backward. Again, electrons you cannot distinguish, so this is fully mirror symmetric because we have nothing in our Hamiltonian that couples the two electronic degrees of freedom. We don't have anything like a spin orbit coupling in there. We also see that double ionization does not play a role here. Yeah, so what can we say on a qualitatively picture here already for our ionization dynamics? Well, we see, or you can believe me, that there is a forward-backward asymmetry. When we now look only at X, for example, I said it's sufficient to just look at one coordinate. We have this kind of double stripe structure. So this means that if the X electron gets emitted of our molecular model system, it's not like it gets emitted and the Y electron stays at one position. For example, here in the down channel, like left-hand side, we see that the Y electron can also be on the right-hand side. So there was a charge transfer or electron migration. And we can see that these processes have some substructures, and we can also see that these things are happening on different time scales. There are time delays mentioned here because here at 3 femtoseconds, we have this down channel and forward far more evolved than the up channel here. Okay, so we can already say that there will be some electron-electron, electron-nuclear correlation even, which are leading to different pathways during the ionization, and not just our single active electron picture that one electron gets ionized and the rest stays, and the parent ion electron stays in its original position. So what we are doing now is we are using the fact that in the beginning I told you we are using the concept of potential energy surfaces to ease our analysis. And that's exactly what we are now doing. And this is very in line with what I showed you in the introduction, what Misha Ivanov is doing for the atomic systems. So as said, with our XUV pulse, we ionize basically a bunch of 1 electron parent ion states. And now we want to have a look at how these states are populated during the XUV attosecond ionization. And we do this by taking our full wave function, our full 3-dimensional wave function, and by projecting out the bound 2 electron part, so this down here. And then we project this wave function, which we can say, so the parent ion plus continuum wave function, we project this on our 1 electron basis, which we calculated before. And then we can see how these 1 electron states are populated during the XUV interaction. And what we see here is very similar to what we've seen in atoms. So we see that we have, first of all, excited states are populated, meaning we are not just left in the lowest ground state of the parent ion. And you can see that we have these 2 time scales seen in atoms as well. So we have an instantaneous, population of excited states, but we have also pronounced dynamics when the XUV pulse has already vanished. That's shown here. And what our next step is now, we try now, well, that's rather not, it's nice to see that we have shake up and knock up and that we have correlation effects, but now we try to dissect this into specific ionization pathways and try to understand why do we have these different pathways and can you maybe relate this to some more intuitive semi-classical pictures. Okay, to do this, we need some little theoretical tricks. And for this, first of all, we come back to what I said initially. We have the quantum mechanics has the principle that electron is not distinguishable, but it's in this case it's a problem. For the analysis, if you, for example, want to say where the emitted electron is coming from, we can't say this. It could come from X or Y electron. It could come from the right or left hand position. So the first trick and approximation we are doing is that we're using artificial subsystems, as we call it, meaning that this is our full initial density, electronic density. And now we just make our electrons distinguishable by applying a Heaviside function around the mirror plane and creating a subsystem, let's say A and B, in which we can exactly say where which electron lays. For example, subsystem A means that the X electron is on the left-hand side, the Y electron is on the right-hand side. The X is a strongly and the Y the weakly bound electron. And later, when we look in the ionization processes, we always monitor the X electron. So if only looking at the X electron coordinate, we can exactly say where it comes from and where the Y electron stays in the parent ion. And our second approximation is to use a restricted field interaction, meaning we let our XUV pulse only interact with one of these electrons. So in the end, we have 4 calculations basically in the subsystem AB, and each of them only letting interact with the X or the Y electron to differentiate different pathways leading to ionization. Okay, and as I said, we are now only looking what's happening in X direction and forward, backward direction for X ionization, single ionization, forward and backward direction using these 2 systems, these 2 approximations. Okay, so what I show here, this is the full result, the full system, full interaction, meaning none of these 2 approximations I just introduced. And this in forward and backward direction. And here we see the dynamics, we see the population of the parent ion states. Ground state, first, second excited states. And now, as said, we do this for our artificial subsystem and restricted. And I'm fully aware that this is a rather tedious slide, so there's no need to get confused. I try to walk you through this slide slowly, one by one. I'm just going to point out at this point the general organization of this slide, which is that this A and B indicate which subsystem we use. So for example, A meaning X is there, Y is there. And here we indicate with which electron the laser interacted. Meaning here the laser interact with the X electron, which is the electron which gets ionized. and here with the Y electron, the laser interacted with the electron, which stays in the parent ion and is not ionized. Okay, and again, as a reminder, interesting to watch out for the NS2 state, because this one is on the right-hand side, whereas 0 and 1 is on the left-hand side for the parent ion. Okay, we start now with this panel F. So we ignore everything else and just look at panel F. Panel F is a calculation in the B subsystem, meaning the Y electron is on the left side, the X electron is on the right-hand side. And we also interact the laser with the X electron, and we also monitor the X electron getting ionized. And what we see here in the quantum mechanical population of the parent ion state, we see that just the ground state, NS0, is populated in the parent ion, and there's no other dynamics really going on. And this is explainable with, as I said, this little comic semi-classical picture, that the X electron just gets ejected, emitted out of our, ionized out of our molecular system, and the Y electron didn't interact during this process, and it just stays on the left-hand side. So that's why we frame this a direct emission. And the same thing can happen on the left towards the backward direction. And this is the panel C here. This means the X electron interacts with the laser pulse, it's emitted in the left to the backward direction, did not interact with the Y electron. The Y electron just stays on its initial position, which is the NS2 state, if you remember, on the right-hand side. Then we have panel D and E, where again, the X electron here, for example, gets emitted out of the system, but it will have to interact with the Y electron during its ionization. So the X electron will pass the Y electron. And well, first of all, what you see here initially is that the X electron, if it just leaves the system, the Y electron, the parent ion, will stay on the right-hand side, which is the NS2 state. That's what we see in the quantum mechanical results. But as you can already see, there is more dynamics going on. We see here, which we call a knockdown process, meaning that the Y electron will, at some point, will take the place of the X electron, and we'll have a charge transfer. And the same thing will happen in the left-hand side, in the backward direction. The X electron, if it gets emitted, it will interact with the Y electron. And then we have basically two quantum mechanical results. Number one, the Y electron does not really care about the X electron passing it, or there will be an energy exchange, and the Y electron, the parent ion, will be left in an excited state. Here, the NS1 state. Yes, and this would be again a knock up, whereas we saw here the knockdown process, which can also happen in this emission where the Y electron takes the place of the X electron. These four panels, these four pathways were all for the fact that the electron that gets emitted is the electron who absorbed the XUV pulse. But in theory, and what's happening, it can also be the other way around, and that's what we mimic here. It's where the Y electron, we let the XUV pulse interact with the Y electron, but nonetheless, we monitor that the X electron gets ejected. And that's exactly what we see here. So what we see in the quantum mechanical results is that the X electron gets emitted and the parent ion gets populated in its ground state. And this can be understood like a game of pool or billiard. In a very classical picture, the Y electron absorbs the XUV pulse, gets ionized, it scatters, it interacts inelastically with the X electron, and the X electron then leaves the actual molecular system, and the Y electron takes the place of the X electron in its ground state, or again, excited with energy exchange in an excited state. And this can happen in both directions. Okay, so I think we made it through this slide and show that there are different ways we can understand in a semi-classical picture what happens during the attosecond ionization in molecules. And now, of course, in this community, time delays are always very interesting. And so we want to report on this as well. As you might imagine, it is rather tricky to extract absolute time delays in this multi-centered, highly Coulombic system. So we don't do it for now. But we can do reference time delays. We basic reference to the fastest process which is the direct emission of the weakly bound electron. And then we see that the direct emission of the stronger bound electron is 20 attoseconds delayed, which is rather expected. And we can also see that then the emission where the X and the Y electron interact is even further delayed, and the inelastic emission, where we have this billiard pool-like picture, is actually quite a lot delayed. And the same thing can happen in the other direction. Okay, so I've talked now extensively about the electron dynamics, but I'm sure some of you already realized that we have more features in here, because as said, the nuclei is also treated quantum mechanically. And we see here this behavior in the post-ionization dynamics. And this is very well known in the field of quantum mechanics, in quantum chemistry. Here we have avoided crossing in our parent ion. And this transition here is exactly that our wave packet on the nuclear wave packet, in this case, in our parent ion will have evolved after, let's see, 15 femtoseconds towards the avoided crossing, and we will have here a transition between the two states. This can also be seen if you look into the parent ion density. That's the electron, the nuclear density. We see how the nuclei moves to the right-hand side, and then here about 15 femtoseconds, we see a split in the electron density, and that's because as we still remember, the N is 2 states on the right-hand side, the N is 1 state on the left-hand side. So this is actually a non-adiabatic transition, which induces a charge transfer. Okay, so let's have a look at the time. Okay, we're good in time. So what I showed you is our simple molecular model system, which we use to try to mimic single photon, single XUV ionization in an arbitrary molecule with valence electrons. And we used some artificial subsystem in a restricted field interaction to try to relate to semi-classical picture and to discriminate different pathways, which we named following direct, scattered, and indirect emissions. We saw that we have pronounced shake and knock processes, and that we have time delays in these different pathways. So what we can say in general is that the post-ionization in such a molecule is interestingly driven by coherent electronic and a nuclear wave packet in our parent ion, as we have seen for this non-adiabatic transition. Okay, so what is next? We now have this model system, and now we obviously want to understand and control more different situation simulations to understand in more detail, especially the role of the nuclei. And as mentioned before, one thing would be to have absolute time delays. That's something which we have to work on. And another step now is how can we control how we, depending on the pulse length and also on our wavelength, how will our electron correlation driven processes change? And we want to have, since we now have this very exact with TDSE, we want to do some method comparison with that as well. And to have a few more minutes left, I just want to very briefly go into slight more detail what we are planning to do here and what we already did here in our regarding a method comparison and how we want to look into the control in the continuum. As you might imagine, this lengthy analysis, which took me here 30 minutes to present, is would be rather tedious to do every time and not nicely to really grasp if you want to do this for every parameter set. So what we are using now in the future is the forward-backward symmetry as a kind of correlation indicator, because the forward-backward symmetry arises because the two different bound electrons use different pathways and they are differently pronounced. And they are all due to electron-electron correlation. So we will from now on always use this forward-backward asymmetry in a way to understand our correlation. And then we did basically the same analysis with different methods, our TDSE, perturbation theory, Hartree-Fock, time-dependent Hartree-Fock. And what we basically see there is that only TDSE or exact perturbation, or 2D perturbation theory are really able to reproduce our asymmetries, which we see through a different range of pulses, and that Hartree-Fock, as expected, but also time-dependent Hartree-Fock, are not able to reproduce our correlation effects. And well, let me do some more about trying to understand how continuum resonances rely on pulse length and wavelength, but this is something for a different talk. Or I'm happy to talk about this or discuss this in the Meet the Speaker session. So now things we want to do then is to look more in the nuclear electronic coupling during ionization. Since we have our quantum mechanically treated nuclei, we can look into electron decoherence, spin effects, of course, and then into the relation to real molecules. So I want to finish with thanking you for your attention. And I want to thank Professor Dr. Stefanie Gräfe for the topic in her group, and Dr. Alexander Schubert, and Jakob Runke, who is a bachelor student doing a research project with me on the nuclear electron coupling during ionization. Thank you very much, and I am looking forward to any questions.
Okay, thank you for the presentation. So now we have some time for questions. So please raise your hand if you have questions. I'm trying to see some. I don't see any hands for now, so I'll ask the first question. So towards the end, you show, I mean, you compared a different method, and you show that you need to do full correlation and so on to get this asymmetry right. But what if you do time-dependent CIS? If you just include single excitation? Because, I mean, it went a bit fast for me, but in the list, it was mostly a Hartree-Fock, right, or some perturbation. But if you do only singles, which should be not too expensive, how would that be?
So yeah, in principle, I mean, we can try any kind of theory on that. That was just basically the first ideas, because you can easily do like a numerically exact Hartree-Fock on there and create two orbitals and one electron wave functions, and then do this also time dependent. On the other mind, I'm not sure how easy to do CIS on this, but definitely something I can think about. Okay, but just so yeah, you don't know if you really need the two electron correlation if to get this right. Okay. Are there questions? No, I don't see any other questions. So maybe we can, we still have time, so we can wait 1 or 2 minutes to see if questions come up. Just maybe I can answer to Gilbert for the, yeah, we saw that you disappeared, and we thought that maybe you can ask your question to Vincent during the Meet the Speaker session that we just follow. Okay.